Hello everyone. So in the previous video we have seen the definition of the Dirac delta function or distribution as any function f who satisfies simultaneously these two conditions, these two constraints. So we have also given three different representations for any Dirac delta function. And now in this video I will not consider necessarily the fact that f is positive, because there's no reason with using these two conditions that f is also positive. No, there's no reason for that. And now I will give you another. So if you remember, the first one, a rectangle function, the second one, a Gaussian distribution or a Gaussian random variable, and a Cauchy distribution. But now I will consider another function which is not positive, in fact. And I will start, so this is the fourth representation, and I will start with the definition of a function f which is called the Sinc function, Sinc of x. So as you remember, this function is defined as sine of x over x. The plot of this function from one side is interesting, in fact, because of the fact that in fact this function is not defined at the origin, but its limit is equal to 1. Sorry, before plotting this I will give you a formula. In fact, we can show that the integral of this function of sine of x divided by x dx, so the integral of the Sinc function from minus infinity to plus infinity is equal to pi. Now I will not try to show this this formula, but I will prove another much more complex integral in a bit later. So now from this theorem, from this formula, in fact, I can say that the integral of sine x over pi x dx from minus infinity to plus infinity is equal to 1. So that this function could be interesting for us. Now if I plot this function, so sine of x over pi x, the limit of this function when x tends to 0 is 1 over pi, and the points of intersection will be pi, 2 pi, 3 pi, minus 2 pi, and the function is symmetrical with respect to the y-axis, so that I will have something like this with clearly a decreasing amplitude when we increase the distance with the origin. So this is the typical plot of the function sine x over pi x. But now I will add another parameter to this function, and I will define a function f of x and t like sine of tx over pi x for positive t. First of all, I will show you that the integral from minus infinity to plus infinity of this sine of tx over pi x dx is equal to 1 for any arbitrary positive value of t. So this formula, which is much more complicated to show than this one, because here t is equal to 1, but now we have another parameter which is t, so independent of the value of t, this integral is always equal to 1. And now the objective is to show this formula, and in order to show that I will use the concept of the Laplace transform of any function. So if you remember, the Laplace transformation of a function of t is defined as the integral from 0 to plus infinity of exponential of minus st ft dt. This is the definition of the Laplace transformation of any function, which give us another function of the variable s here. So I will calculate the Laplace transform of this function, and the value of this function will be the inverse Laplace transform of the result. So now I will calculate, as I said, the Laplace transform of the integral from minus infinity to plus infinity of the sine of tx over pi x dx. This is in fact the integral from 0 to plus infinity of exponential of minus st times the integral from minus infinity to plus infinity sine of tx over pi x dx, and finally d of t. If I change the order of integration between the x and t, I can write the result as the integral from minus infinity. So first of all, I integrate with respect to x rather than t, and I will have dx over pi x 0 to plus infinity exponential of minus st sine of tx times dx. Sorry. And as you see, this is exactly the Laplace transform of the function sine of tx. And we know that the result is x over s2 plus x, sorry, s2 plus x2. And if I replace the result here, I will have the integral of x dx over pi x, in fact, times s squared plus x squared. And if I cancel out these x's, I will have the integral dx over pi times s squared plus x squared, and the result is 1 over pi times 1 over s, sorry, I have always this problem, 1 over pi times 1 over s times inverse tangent of x over s, from x equal to minus infinity to the plus infinity, so that this will be pi half minus pi half, and this result in fact is equal to pi, and if I cancel out these two pi's, I will have 1 over s. And now I know that the Laplace transformation of this function of t is 1 over s, so that the result, the function itself, in fact, from minus infinity to plus infinity, sine of tx over pi x dx is equal to the inverse Laplace transform of 1 over s, which is exactly equal to 1. So I've shown the formula, and now that I know that this function can be interesting because of the fact that its integral is equal to 1 from minus infinity to plus infinity, I will consider its plot, in fact. So if I plot this function, now I'm talking about the function sine of tx over pi x. I know that the limit when x tends to 0 tends to t over pi, and that the roots are now divided by t, so that I will have pi over t, 2 pi over t, from this side minus pi over t, minus 2 pi over t, etc. And the plot of the function is exactly like sine of x over x. But now I am observing that when this t goes to plus infinity, this height will go to the plus infinity. These roots will all tend to the origin, in fact, these two at least. And I will have something like this. And this is exactly so the limit of sine of tx over pi x when t tends to plus infinity. Sorry for that. This limit is exactly the Dirac delta function at not the point x0, at the origin, in fact, delta of x minus 0. So how can I extend this function to the case of delta of x minus x0? You can show yourself that the limit of sine of t times x minus x0 divided by pi times x minus x0 is when t goes to the plus infinity is exactly the Dirac delta function around the point x0. So this is another representation of the Dirac delta function. So another function which is now not always positive. So this is not a probability distribution function. And now I will try to give another representation for this function, or for this function, in fact, for the both of them. If I consider now the integral, this integral, in fact, 1 over 2 pi times the integral from minus t to plus t of exponential of I k x dk. This is really straightforward to calculate. So this is 1 over, the integral is with respect to k, so that this is ix exponential of I k x from k equal to minus t to plus t. And if I replace, I will have 1 over, I will consider pi times x here, 2i here, and I will have exponential of I tx minus exponential of minus itx. And using the Euler's theorem, this is 2i times cosine of tx, such that this whole thing is equal to the sine of tx, and I will have sine of tx over pi x. This is the function that I have defined at the beginning of this video. So I've started with sine of x over pi x, and then I've generalized, I've added this parameter to it, such that this is a function that I've considered at the beginning. And I know that the limit of this function when t tends to plus infinity is exactly delta of x. So if I take the limit of both sides of this equation, this side and this one, I take the limit when t tends to plus infinity. Here, the limit when t tends to plus infinity. This integral is exactly 1 over 2 pi integral from minus infinity to plus infinity exponential of I kx dx, and this is exactly the delta distribution of x, delta x. This is another representation of the Dirac delta function, and if I generalize this definition, you can show yourself that we have something ik times x minus x0 dx is equal to delta of x minus x0. So this is, especially this one or this one, they are the same, is called the integral representation for the Dirac of the Dirac delta function. Delta function. So now I will use this representation, this integral representation for the Dirac delta function, in order to define the Fourier transformation of any function. So now I will consider from one hand this integral representation of the Dirac delta function. So the 1 over 2 pi from I should just add another point here, that the result of this integral, if you put here plus or minus, is exactly the same here, so that if here I will put plus or minus, is exactly the same delta. You can verify that by yourself. Also here, plus or minus will change nothing in the final result. But now I will consider this integral from minus infinity to plus infinity ik x minus x0 d of k. We have seen that this is nothing, this is exactly delta of x minus x0, and in the first video I've talked also about the most important property of any Dirac delta function. So f of x prime times delta of x minus x prime d of x prime is equal to the value of the function f evaluated at the point x here. So this can be x prime minus x or x minus x prime. So now if I replace this function, this delta function, from this equation into this equation, in fact, so I will replace this integral in this formula. I will have 1 over 2 pi times the integral from minus infinity to plus infinity f of x prime d. So I will replace this x0 here by x prime, in fact, sorry, times, in fact, now I will have a double integral from minus infinity to plus infinity times the exponential of ik x minus x prime dk dx prime, and the result is f of x. So now I will decide to decompose this coefficient to something multiplied by something. So a constant a multiplied by a constant b, Now I consider, for example, the constant a and b both to be equal to 1 over square root of 2 pi. And I will define the function f of k as, for example, one part, so 1 over square root of 2 pi, times all the parts of this integral containing x prime. So f of x prime exponential of minus I k x prime d of x prime from minus infinity to plus infinity. So if I define this f of k, I will have f of x will be the other part. So if a is equal to 1 over square root of 2 pi, the other part is exactly the same because of the fact that the multiplication of these two constants is exactly 1 over 2 pi times the integral from minus infinity to plus infinity of f of k exponential of plus I kx times dk. So these are the Fourier integral pairs. In fact, if I replace this x prime by x, in fact, this integral from minus infinity to plus infinity takes the function, the origin function f of x, and changes the variable from x to another variable k in the Fourier domain. And we will call, in fact, this function the Fourier transformation of the function f of x. This is, in fact, one of several different types of the Fourier, of the integral transformation, in which we have the integral of a kernel. For example, this kernel for the Laplace is exponential of minus st, but in Fourier domain is exponential. In Fourier transformation is exponential of minus a kx. So this takes a function of x and brings it and transform it to another function, the Fourier transform, in fact, of the f at the variable k, which has the dimension of the inverse of x, in fact. And here we take the inverse Fourier transformation in order to calculate the function itself. So this is the inverse transformation of the Fourier transform, which gives the function itself. And at the end of this video, I will just emphasize on the fact that I can change this relation here, this plus or minus. This can be plus or minus, so that at the end here, if this is minus, this should be plus. And similarly, if we define the Fourier transform of the function f as 1 over square root of 2 pi minus infinity to plus infinity f of x times exponential of plus I kx dx, if we define like this, the inverse Fourier transformation will be the same, but now the kernel, the exponential, will change the sign. So here minus plus or plus minus. These can be also the Fourier integral pairs. And also I emphasize again on the fact that this 1 over 2 pi can be decomposed as you want. So here I decided to put 1 over square root of 2 pi, 1 over square root of 2 pi. You can decide here 1, here 1 over 2 pi, or 1 here and 1 over 2 pi here, or any other choices that can be imagined. So as you saw here in these two videos, I've talked about the Dirac delta function, its main properties, the integral representation of it. I've put this representation into this property, and I will have the Fourier integral theorem. In fact, this is called the Fourier integral theorem. So you can now you know now the definition of the Fourier transformation of any function in one-dimensional. In fact, x and k are one-dimensional variables. In the next video, I will talk about the Fourier transformation of some of the most important functions f, which are interesting in the literature. Thank you very much for your attention.